be in time, so maybe let us start with this session. So welcome everybody in the network session. Our first speaker is Adam Błoch, and he will talk about an overview on hyperbolic systems on networks, transport, telegraph, and more. And I'm curious to hear whether they differ. Please, Adam.
Thank you very much for the introduction, and I would like to also thank the organizers for the possibility to present some of my results. So I can see that some of you were on my talk on the last year's edition of this conference, so even the chairman is the same. So a piece of information for you, I'm just finishing that talk because there were some open questions. So this is an overview talk, but it is based on some results that I obtained together with my PhD supervisor, Jacek Banasiak, who unfortunately cannot be here today. But we would like to also acknowledge contributions by many other authors. Okay, so the starting point is usual for this topic. So we consider a metric graph. This is a graph where each edge is identified with the unit interval through a sufficiently regular function. And on each edge, we consider a hyperbolic system, which can be of arbitrary but finite dimension. We developed this theory in the case of two equations, but because here I don't need to deliver any proofs, so I can go a little bit crazy. So some examples of such systems, of course, transport equation. This is an example of one equation on an edge. Then some examples that inspired us the most. These are a system of two equations, Saint-Venant, or known also as shallow water equations, or the telegrapher's equation, but also first order Timoshenko beam, which is usually a system of two second order equations, but it was shown that it can be reduced to a system of four first order equations, so it perfectly fits into our framework. Okay, so the key idea here is to diagonalize each system, so that we assume that these matrices, or rather matrix functions, are diagonalizable with non-zero and distinct eigenvalues of +C1, so that our system can be written in a diagonal form, and in this form it decouples with respect to the derivatives. And after such a diagonalization, each function describes a flow in a constant direction, either from 0 to 1 if the corresponding eigenvalue is positive, or from 1 to 0 if the corresponding eigenvalue is negative. And some remarks at this point. So if we have a pure transport problem, then we can a priori parameterize all the edges either flow-wise or counter-flow-wise, if you prefer, so that all flows occur either from 0 to 1 or from 1 to 0, and this is impossible in general case. A technical remark is that this matrix NJ tilde induces a bounded perturbation in any LP space, so we will discard it in further considerations, but we will go back to the full problem at the end of my talk. And as I mentioned, this system is decoupled with respect to derivatives, so the essential role is played by the boundary conditions. So we decided to consider a local boundary conditions and follow some paradigm concerning general one-dimensional systems, which can be found in the literature. And this paradigm says that at each point of the boundary, the outgoing data must be determined by the incoming data. And I would like to emphasize that this is not the only possibility. For example, if you are working in L2 setting, then you can try to pose such boundary conditions that the corresponding operator has some required properties. So, for example, self-adjointness. And if you would like to see such alternative approach, then I refer to this paper at the bottom of this slide. We are focusing on local boundary conditions, and in our case, the boundary consists of the vertices of the underlying graph, and locality means that for a given vertex, we consider only these functions that are posed on the edges adjacent to this chosen vertex V. Okay, so let us take a look what was done for the transport equation. This is a problem which I believe was first considered in 2005 by Marietta Kramer and Esther Shikolia. So we have a pure transport problem, and the boundary condition of this form. This boundary condition basically expresses the Kirchhoff's law in vertices, but because we can have more than one outgoing edge at a vertex, then we must put some non-negative weights. These are the coefficients Wij, and we assume that they sum up to 1 for each vertex V. We can have some amplification absorption coefficients, and the structure of the graph is encoded in the incoming and outgoing incidence matrices. These are the coefficients phi minus and phi plus. It was shown that the boundary condition can be written in an equivalent form using only one matrix, which encodes both all the weights and the structure of the graph. So our problem becomes like this, you can see here. And of course, we are interested in the generation of a semigroup, so the associated abstract Cauchy problem is determined by an appropriate operator. Okay, and a few words about the well-posedness. So in the pioneering paper, Kramer and Shikolia considered the case of constant velocities along the edges and the stochastic matrix B. And the generation of a semigroup was proven in L1 setting. They used Phillips' theorem for dispersive operators. 2 years later, Matra and Shikolia adapted this approach to also x-dependent velocities. There was a few years break, and in 2014, Jacek Banasiak, together with his then PhD students, considered slightly more general boundary condition with this application and absorption coefficients, which made the corresponding operator not necessarily dispersive, so they used Arendt-Batty-Robinson theorem for resolving positive operators, and they also proved that this operator generates a semigroup if and only if the underlying graph has no sink. And 2 years later, another PhD student of Jacek Banasiak adapted this approach to an arbitrary matrix B, because in this formulation of the problem, B need not to come from local boundary conditions on a graph, but in general, it can be an arbitrary matrix. Okay, so now let us move to our general hyperbolic systems. So we assume that at least on one edge we have more than one function. By JV, we denote the set of indices of the edges which are adjacent to V, and by KV, we denote the number of outgoing functions. Outgoing functions at V, because as I said, after the diagonalization, thanks to our assumptions, each function describes flow in a constant direction. So at a given vertex, some functions are outgoing from this vertex, some are incoming to this vertex. So the number of the outgoing functions depends basically on two things. This is the parameterization of the edges and the signs of the eigenvalues. which are transport velocities on each edge. Okay, so we take a vertex, we take a vector of functions which are posed on the edges adjacent to this vertex. We take a matrix of suitable dimensions, and we consider the boundary condition in the form of a homogeneous system of algebraic equations. This is done for the original variables before the diagonalization. We decided for this approach because we believe it is slightly more general, but of course, this boundary condition can be written also for the diagonalized system. And in this formulation, it can be easily split into the outgoing and the incoming part. But after a moment of reflection, we came to a conclusion that this boundary condition means that we basically need to distinguish functions from the direction of the flow point of view. So what can we do is to gather all the functions describing a flow from 0 to 1 into one vector valued function, then do the same for the functions which describe flow from 1 to 0. And then after some permutation of rows and columns of the boundary matrices, our boundary condition can be written in the following form, which means that our initial boundary value problem becomes quite similar to the transport problem. And what's more, it was shown that the invertibility of the matrix psi out, which means solvability of the boundary condition with respect to the outgoing values, is in fact necessary for generation of a semigroup. And we can write our boundary condition in an equivalent solved form. And again, in this formulation, in general, we can consider any matrix B, which does not necessarily come from local boundary conditions on a graph. What about well-posedness of this problem? So in 2010, Zwart et al. And other proves that indeed such an operator generates a semigroup, but they did it by control theory methods, and they proved it first in the space L2 and then extended it to any LP excluding infinity. And we developed an alternative purely semigroup theoretic proof. And first we did it in L1 space, and then extended to an LP using an explicit formula for small t and direct estimates. And here I would like to emphasize that this approach to boundary conditions does not exclude the generation of a semigroup in the case if the underlying graphs have some sinks. Okay, so now let us move to the asymptotic behavior of the semigroup. And again, first the transport case. And this theorem probably does not catch all the details that have been proven throughout the years. But I think this is a quite fair summary of the asymptotics of the transport semigroup. So we have a semigroup which solves our transport problem with velocities which are constant along the edges. We have an assumption which says that our transport velocities are linearly dependent over rational numbers, and under this assumption we can show that we can decompose the space L1 into some subspaces such that on one of the subspaces the semigroup is periodic, and the period is equal to the index of impermittivity of the matrix B. On other subspace it is exponentially stable, and on the last subspace it is nilpotent. It may happen that some of these subspaces is the trivial subspace. And the first part of this theorem is valid independently of the graph structure. So we can have a general matrix B, But if this matrix comes from Kirchhoff's conditions on a graph, then we can additionally relate the period of the semigroup to the structure of the cyclic part of the underlying graph. Again, a few words about the proofs of this theorem in various situations. So again, first Kramer-Shikolia in 2005, they used spectral theory, and this is probably the first idea which comes to mind when you want to investigate the asymptotics of a semigroup. Then 2 years later was shown that if this assumption LDQ is not satisfied, then there are no non-trivial periodic solutions, which means that if we want to have some interesting regular behavior of our semigroup, then this assumption LDQ is not really a restriction. In the same year, Dorn showed that for the transport semigroup with unit velocities, so this semigroup can be expressed explicit. So we have an explicit formula for our semigroup, and again there was a few years break, and in 2014, Banasiak and Namayanja first showed that under this assumption LDQ, the problem can be reduced to an equivalent one with unit velocities. I will say about it a few words more in a moment. And then they investigated the long-term behavior of the semigroup on reducible networks, and they used the spectral decomposition of the boundary matrix. Okay, so what can we say about the asymptotics of our semigroup, our general hyperbolic semigroup? So first, we would like to use some explicit formula which we are able to find, but this formula can be found only in the case if all the velocities are constant and the same. So basically, it means that we need to reduce our problem to the constant speed case, and we will reduce it to the unit speed case. So we introduce a counterpart of this assumption LDQ, which in this case of x-dependent velocities can be expressed using some upper integration limit function. Then we make a change of variables, and this change of variables converts our problem to an equivalent one with unit speed, but the equations are posed on intervals of different lengths. But thanks to our assumption, these lengths are of natural numbers, which means that we can divide each of these intervals into intervals of unit lengths, and then translate everything into the interval 0, 1. And this can be formalized by an operator, which provides us with some similarity relation between the semigroup with x-dependent velocities and between the semigroup with unit velocities. And this is basically what was done for the transport problem, but this construction for x-dependent velocities was not described in the literature. And this is easily to explain from the graph point of view, because what we are doing is that we are lengthening the edges of the graph, and then we cut them into unit intervals by introducing some artificial vertices along these edges. But of course, the construction is valid also in an abstract setting. Okay, so if we have already our problem with unit speeds, so by the method of characteristics, we can obtain an explicit formula for this semigroup. And on one hand, we should be happy that we have this explicit formula, because probably it would be easier to it will be easier to investigate the long-term behavior. But on the other hand, as you can see, there are some problems. The first problem is that this natural parameter, which is responsible for successive powers of the boundary matrix and for keeping the arguments of the functions between 0 and 1, is not the same in the whole formula, or equivalently, we could say that if we take m equal to n, then the top formula is valid in a different interval than the bottom formula. And the second problem is that we need to know particular blocks of successive powers of the matrix B, which means that we cannot apply the spectral decomposition directly. So this is the point where we must turn to the reparameterization of the edges. We introduce an operator which leaves the first component of our vector valued function unchanged, but for the second component, it makes a change of variables x to 1 minus x, which from the graph theoretical point of view can be explained as reparameterization of the edges on which the flow occurs from 1 to 0. And this operator gives us a similarity relation between our general hyperbolic semigroup and the transport semigroup. And here, as you can see, the matrix B appears in a let's say consistent ways we can apply the spectral decomposition. And this is exactly what we are going to do. So first, some general properties of this semigroup. We take any eigenvalues of the boundary matrix B, and we define a family of linear and bounded operators simply by replacing the matrix B by its part corresponding to these eigenvalues. So we have these eigenvalues. We have the spectral projections onto the right eigenspaces corresponding to these eigenvalues. And because the eigenvalues need not be semi-simple, then we can also have some matrix-valued polynomial in N, but the degree of this polynomial does not exceed the algebraic multiplicity of the corresponding eigenvalue. And what can we show is that such a family is a semigroup in the sense that it satisfies the semigroup property, and that the range of the operator S lambda 0 is a closed and invariant subspace. Is closed and invariant under our semigroup, which means that if we restrict our semigroup to this subspace, then we obtain a C0 semigroup. If we assume more about the structure of the spectrum, then we can say more. So now we assume that the eigenvalues, that the spectrum of the matrix B is divided into two parts. The first part consists of eigenvalues which are smaller than 1 in modulus, and the second part consists of semi-simple and cyclic eigenvalues. And under these two assumptions, the number of the semi-simple and cyclic eigenvalues is basically the index of impermittivity of the matrix B. And it is worthwhile to say that these assumptions E1 and E2 are automatically satisfied if B is a stochastic matrix, which means that the redistribution in vertices is conservative, and this follows easily from the Perron-Frobenius theory. And now we can decompose our semigroup into a sum of two semigroups, and both of these semigroups have the structure of our family S lambda, which I introduced in the previous slide. Okay, and now the main theorem. So if we assume only E1, then we can decompose our space into two subspaces which are invariant under our semigroup, and such that our semigroup behaves asymptotically as the semigroup S1, which corresponds to the cyclic part of the spectrum of the matrix B. this basically means that the semigroup S2, which corresponds to this eigenvalue smaller than 1 modulus, is exponentially stable. We can write down an explicit formula for this limit semigroup, and if we additionally assume E2, then our limit semigroup becomes periodic, and the period is equal to the index of impermittivity of the matrix B. So this theorem is quite similar to that for the transport semigroup. It is written in a slightly general form, I believe, and it is done in any LP space. So the transport equation was investigated only in an L1 setting. Here, this theorem is valid in any LP space, and it also shows that the asymptotics of the semigroup does not depend on the value of the exponent P. Okay, so as you have probably noticed, our general hyperbolic problem is quite similar to the transport problem. So there is a natural question: does it make sense to consider such general hyperbolic problem in the sense that we could make the change of variables at the beginning, we could reduce everything to a transport problem, and say that everything goes in the same way. So does it make to consider such problems? No. I don't know if there is only one good question to answer to this question. On an abstract level, I think yes, we could restrict ourselves only to transport problems, and especially for the generation of a semigroup, it doesn't make much difference. But what about the asymptotics of the semigroups? Well, these are problems which come from some applications, because as you have seen, we have transport, we have telegraph, we have Timoshenko, and so on and so on. So maybe sometimes taking a bit longer way may result in a better understanding of the process. And if we restricted ourselves to only transport problems, then in the end we would have to translate everything back into the original problem anyway. And there is one more thing. Let me show you the mistake that we made. And fortunately, we realized early enough that we made such a mistake. But this shows that sometimes going too deep into abstraction may be misleading. Okay, so what I mean, let us consider a perturbed transport problem. So we have this zeroth order term, K is a matrix, and it was shown that we can convert such a problem into an unperturbed transport problem, such that this perturbing matrix K appears in the initial condition and most importantly in the boundary condition. But this is a transport problem, and we know an explicit formula for the semigroup for this unperturbed transport problem. So here we also know an explicit formula. So this substitution induces a similarity relation, and we simply need to exchange the matrix B with B times e to the power K, so the exponential of the matrix K. So maybe this formula is not very...
Adam, just you have 1 more minute just to tell you.
Okay, so I'm just finishing. Thank you very much. So now a simple conclusion. If we know the formula for our perturbed transport problem, then we can consider a perturbed general hyperbolic problem. And since we have this operator V, which induces a similarity relation between general hyperbolic and transport problem in the unperturbed case, so in this case it should be the same. So we also have an explicit formula for this perturbed problem, but this isn't true. And why? If this similarity relation 5 held, then we would also have the equality of the generators of semigroups. And this equality means that the action of the operator of the matrix K, understood as the pointwise multiplication, would be the same as if we wrapped this matrix K into the operator V, and this is not true. This is true only in some special cases when K is diagonal, or at least Błoch diagonal. So I think this shows that sometimes going too much into abstraction maybe a little bit misleading. Okay, so some references at the end, and thank you very much, and I will be happy to answer some questions if there are any.
Thank you.